So this takes us through the hundreds and hundreds of years. Okay, this one, I like this chart because it gives you a little feel for what was happening. It says the transition from ancient astronomy to the birth of modern scientific astronomy. You got here Copernicus, 1470 to 1543. 1543 is when he passes away. And then at the same time, other interesting things are happening. Michelangelo, the Magellan voyage around the world, Luther, Leonardo da Vinci, Columbus. So kind of other things, interesting things are happening. Now, after Copernicus dies, then Tycho Brahe is born a couple of years after that. We're going to see what his view was. Tycho Brahe observes a supernova in 1572. He writes about it. He becomes famous. Then he does 20 years of observation on the island of Haveen. Then Kepler comes along. Tycho Brahe hires Kepler in the year 1600. Kepler is his student. Kepler uses the observations that Tycho Brahe had done to come up with his 3 laws of planetary motion. Law number 1 and 2, 1609. Law number 3, 1619. Those are the laws that we'll be studying. The planet's motion is elliptical. Okay, Kepler was the one who came up with that. 1609, 1619. Now, when Kepler is doing this, along with Tycho Brahe, he's working with Brahe, he's using his data. Galileo in Italy is doing his stuff. Galileo is writing a sidereal messenger, 1610, and he's writing his big book called the Dialogues. Dialogues, 1632. So we're going to see what he did. After he wrote that book, 1632, he was imprisoned in 1633. He spent the rest of his life in home imprisonment. So 1633 to 1642, roughly about 9 years, he was imprisoned and he died there. In 1992, by the way, the Catholic Church officially said sorry to Galileo about 300 years after his death. So why was he imprisoned? Because he was vouching for the heliocentric model, that the Earth is going around the sun instead of the Earth being at the center. The Catholic Church said, no, if God is there, God should build the Earth. The Earth should be at the center. Why should it go around the sun? Okay? So that was their view. After Galileo died, Newton was born. His spirit went into Newton, a lot of people said. He had the same charisma and same scientific motivation and desire that Galileo did. And of course, Newton said, I'm building upon the shoulders of others, okay, upon the shoulders of giants. So he's building on Kepler, Brahe, Galileo, Copernicus, and then Newton does his discoveries of the law of gravity and the motions of planets. He writes the big book called Principia in 1687. Okay? Okay, now let's see Copernicus's model of the Copernican model. Remember I said Aristarchus was called the Copernicus of antiquity. So Copernicus revived this theory. Okay? Nicholas Copernicus began to revive the heliocentric model of the solar system. He revived it. You see, he didn't start it, but he brought it back. Here are the features of his model. The sun is the center of the solar system. So he takes the sun, he brings it to the center. Mercury, then Venus. So the sun is the center of the solar systems. The stars are stuck on the celestial sphere. So he's got the stars here. That part is wrong because he assumes the celestial sphere concept is true. Okay? And then the planets go around the sun. Mercury is the closest planet. Venus, second closest. The reason he knows Mercury is the closest is because when he observes Mercury in the sky, it moves faster day by day, day by day. Venus moves a little slower day by day, day by day. So he puts Mercury first, then Venus, then Earth, then Moon, Mars, Jupiter, Saturn. Those are all the naked eye planets. Okay? So then The planets make circular paths around the stars. He doesn't quite know that the orbits of planets are elliptical yet. Kepler is going to come out with that theory later. Okay? Two planets' orbit are inferior to us. What do they mean by inferior? We don't mean like a psychologically they feel inferior or whatever. It just means that their orbit is smaller than ours. And then three planets are superior than us. Their orbit is larger than ours. Okay? Three planets are superior to Earth, Mars, Jupiter, Saturn. Remember, I said no one discovered these. These are the naked eye planets. The planets closer to the sun move faster. Why do they move faster? Well, we now know, right? He didn't know, but we know. Why do they move faster? Smaller orbits, and also something that starts with the letter G. Gravity. The sun's gravity is stronger on them. Did he know about gravity? No. He just observed the planets day by day. They move faster, so he said, I'm going to put those closest to the sun, the ones that move fastest. Okay, here is how he explains retrograde motion. Remember, I said, according to Ptolemy, retrograde motion, the planets will move backwards once in a while. They happen to make two paths. According to Copernicus, retrograde motion is only an apparent backward motion. The planets don't actually move back. They look like they're moving back. Okay? It's only an apparent backward motion. Okay? So retrograde motion is caused, let's put this picture up here. Retrograde motion is caused when the Earth passes a planet which is in conjunction with it. That means it is on the same side of the sun as the Earth is. We'll study what conjunction opposition mean in a few minutes, but let's focus on this now. He drew a picture like this to illustrate why retrograde happens. So let's say the Earth is in this position at month number 1. Suppose month number 1 stands for January. Okay, January. Month number 1. Suppose Mars is in this position in January. Where will Mars appear to be in the sky? Draw a line. Mars will appear to be here with respect to the stars. Okay? By the time February comes, Earth is here. Mars is here. Mars appears to be here. Now notice, because the Earth is closer to the sun than the Mars is, Earth is moving a farther distance, you see? Bigger distance. Mars is going slower. So we're starting to catch up to it, right? March. Mars appears to be here. April. Mars appears to be here. So look what it's appearing as if it appears as if the planet has slowed down month by month. Slowed down month by month, and now it's starting to retrograde. Is the planet actually moving backwards? Look at the planet. Is it actually moving backwards? No, it's moving forward. Is it actually doing this? No. Ptolemy thought so. The planet is still going ahead. What's happening is we're catching up to it. Okay? What's the similar analogy I can give you? Let's say you're driving in the car really, really fast, and then you start to see two cars, and then you start to overtake the other car. You see? So if the red car and the black car, the red starts to overtake the black. You see? And then if you're sitting in the red car, it's going to look like the black is going backwards. You see? So in April, it's going to look there. In May, oh, the planet is really retrograding. In June, now the retrograde part of it begins to slow down. In July, what happened? It retrograded, slowed down, stopped, prograde, back to forward motion. You see? And then August, so it's now full gear forward motion. September, okay, and now the retrograde is done. So Copernicus, thank you. This is the exact reason why retrograde happens. It's only an apparent backward motion. Okay, so if you look here, this is another example of this. This one here is showing you a similar picture. Earth's orbit, Mars's orbit, January, it appears here, so on and so on, 3, 4, 5, 6, 7. Then Mars appears to go forward, retrograde, and then back to prograde. Okay, this one here is a good example because it actually shows you the constellations that Mars is going through. You see here, this is the ecliptic, the yellow line. This is the path of Mars. So look what happens. In May 1st, Mars appears to be here. It's entering Capricornus. By June 1st, Mars is at the tip of Capricornus. By July 1st, Mars is starting to go into Aquarius. By August 1st, it's kind of slowing down. Okay? It's slowing down, stopped. September 1st, Mars retrograded. See, from August 1st to September 1st. From September 1st to October 1st, retrograde is starting to end. And then October 1st to November 1st, forward motion again. November 1st to December 1st, again, back to forward. So now it went through Aquarius, and now it's over here. So how many months did the retrograde take place for Mars in this case? It started around August 1st, right? Retrograde, September 1st, around October 1st it ended. So for Mars, retrograde lasts how many months? August, from the 8th month to the 10th month. So that's 2 months. Okay? That doesn't mean a retrograde lasts the same number of months for every planet. So roughly speaking, for Mars, it's about 2 months backward, then it moves forward. Did it actually move back? No. We were just passing it. See? Okay, so this is the actual reason according to Copernicus. Then we'll talk about opposition conjunction on Wednesday, and we'll continue from there. So remember last time we left it at, we were talking about Copernican model of the solar system, the heliocentric model, and we said according to Copernicus, retrograde motion didn't actually happen. The planets didn't actually go back. It was an apparent backward motion. I wanted to start by showing you this clip that also shows this. So you will see here, I'm going to scroll down. So you will see here, Earth is starting to come around. Mars is also coming around, but Earth is catching up to Mars. And then remember the lines that we drew the other day? So Mars will appear to be here, and then here, and then here. So across the different months, this is the west, this is east. Mars will appear to move from west to east as compared to the relative stars. Then during retrograde, it moves from east back to west. I'll run through it twice so you can kind of see it again. So it's moving forward, and then as the planets are revolving, you can see the simulation running. So then they'll draw a line here. Okay, so this is the regular motion, prograde, retrograde, prograde. Okay, so the prograde motion, this is east, this is west. The planets go like this during the regular motion from west to east, from month to month to month. Okay, this is a prograde. And then they retrograde. And then they prograde. So if I were to ask you on the quiz, what's the regular motion of planets as compared to stars? You say from west to east. What's the retrograde motion? From east back to west. Okay? Now to us this may seem like, oh wow, big deal. Why should we credit Copernicus for this? This was for thousands of years one of the biggest issues in astronomy. Why do the planets go from east to west every couple of months, you know? And no one knew how to figure it out. The heliocentric model was the first correct explanation of this, you see, and it took Copernicus to realize this. A huge, huge accomplishment, okay? The other thing I want to take a couple of minutes to explain are these concepts. What does conjunction mean? What does opposition mean? So to understand that, let's rely on this picture. So it takes a little bit of explaining. So you can see here, they are using Venus as an example. So there are two planets that are inferior to us. So the Venus is one example, and then this is Earth. And then Mars, they're using as an example of a planet that's superior to us. So if this is the sun, and you got Venus here, and you got the Earth, and then you got Mars here. So what are the different possible extreme positions that the planets can be? Okay, Venus, for example, can be in inferior conjunction. That means it's between us and the sun. Okay, so this is known as inferior conjunction. So basically what that means is if we draw a line, it's pretty much between us and the sun. The other extreme position that Venus can be, opposite end, superior conjunction. Okay? So superior conjunction. Now, Mars, on the other hand, since its orbit is bigger than us, it cannot be in inferior conjunction. It's on the opposite side. So the reason they call this opposition is because if we look at the sun one way, we have to look opposite way to look at the Mars. It's opposite to the sun. That's why it's called opposition. You see here? So if we look in inferior conjunction, we look at Venus, we look at the sun in the same direction. But to look at Mars, we got to look opposite to the direction of the sun. So Mars can be in opposition. And the other extreme position, superior conjunction, just like Venus can also be superior conjunction. Okay? So they both can be superior conjunction, but Venus can be inferior, Mars can be opposition. Same thing with Mercury. Mercury can be inferior and superior. The other planets like Jupiter or Saturn, they can be opposition and superior. So a typical kind of quiz type question that a professor might ask is, Mars is in opposition. What time of the day does it rise if Mars is in opposition? Remember, it's opposite to the direction of the sun. So when the sun sets, Mars rises, opposite to the sun. So it rises at sunset. That's actually the best time to see Mars, right? Why? Because of course it's dark. Okay? The sun is setting, Mars is rising, it's really dark. So it's two good reasons why it's the best time to see Mars. It's because the sky is really dark. On top of that, look how close Mars is to us in opposition. It's the closest it's ever going to be. You see? You see the distance between them? So it's going to look big in the sky. It's going to look really bright. And on top of that, the sky is dark. It makes for the best viewing. Okay? So if you want to view Mars, read up on the news, find out when is the next time it's going to be in opposition, and then that's the best time you see it. It's sunset, you see it it's rising. And then if the problem says, if Mars is in opposition, what time does it set? What time does it set? Then it sets at sunrise, okay, opposite of the sun. How about when Mars is in superior conjunction? Well, it's exactly in the same direction as the sun, except it's just behind the sun. Okay? So what time does it rise if it's superior conjunction? It rises at sunrise. So when the sun rises, it's behind the sun. It's the worst time to see Mars. It's the worst time to try to see it. Because essentially when the sun rises, it's tracking the same path as the sun. It's behind it. The brightness of the sun is going to make it impossible to see Mars. It's going to rise at sunrise, set at sunset. Impossible to see it at superior conjunction. So superior conjunction, worst time of the day to see. In opposition, the best. How about inferior conjunction for Venus? Okay, what time does it rise? After a while, you'll get the idea and you can answer it, you see. If Venus is in, so we'll start with inferior conjunction. What time does it rise? Well, it's still in the same direction as the sun. Okay? The only difference, it's in front of the sun. So sun rises, and if the sun is my left hand here, the Venus will be in front of it. It will rise. It rises at sunrise, sets at sunset. Okay? Can you see it? Not pretty much unlikely. So if Venus is inferior conjunction, what time does it rise? Sunrise. What time does it set? Sunset. Okay? So the conclusion is inferior conjunction, superior conjunction is the same in terms of rising setting. The only difference is inferior is in front of the sun, superior is in back of the sun. Okay? During inferior conjunction, it's possible that you have an event that happens that's known as a transit during inferior conjunction. That's when the planet is coming between us and the sun. Imagine this is the sun, the screen is the sun, and you're looking at Venus. It's going across the sun, transiting the sun. Okay. So imagine for a second that the projector is the Earth, the screen is the sun. Okay. So that's Earth, that's the sun. If Venus is down here, it's still inferior conjunction between us and the sun, right? But it's not really going through the sun. It's a little below. So inferior conjunction doesn't have to lead to transit. If it's below, it's not going to transit. You see? If it's above, it's not going to transit. But if it happens to cross the sun, then that's a transit. Would you be able to see that with your naked eye? Oh, there's Venus going through the sun. Oh, no, you need a really good filter. First of all, you can't look at the sun. It's so bright. But if you have a good filter or a good telescope, you can see the event transit, and you can see Venus transiting. Last June, I think it was 12th, it's about almost a year ago, I took my whole class to Griffith Observatory because the last transit was going to happen, okay? The last transit of Venus. The way that it works is it happens every 8 years and then 105 years later. Then 8 years, then 105 years later. There's a predictable pattern. So it happened 2004, it happened 2012, then it's not going to happen till 2117. So I told my students, unless you're going to live really long, this is the last chance that you're going to see it, 105 years, right? So all of us, we went, and there were hundreds and thousands of people packed in Griffith who brought their telescope and stuff. So it was wonderful. The cool thing is that we can predict this, isn't it? We can predict the 8 years, the 105 years, all the computer technology we have and the science and the math and everything, and our predictability power is just amazing. And we were right there, they told us, okay, at 2:59, for example, it's going to start crossing the sun. And we're looking, and lo and behold, it's crossing the sun, okay? So it was a really amazing event. Okay, so now let's go back. The other issue that astronomers had to explain, any solar system concept had to explain, was why are Mercury, Venus at nighttime, why are they only visible in the western sky? So you look in the west, you see them only west, you can never see them up here, you can never see them opposite of the sun. And the way that Ptolemy had explained it, he made this imaginary line deal, and he said, okay, the epicycles of Venus and Mercury are stuck on that for some reason. According to the correct model, the Copernican model, you don't need this weird imaginary line. Okay? You only need a little bit of logic and a little bit of geometry to figure this out. So let's see this picture so you can see. Okay, if you look, geometrically speaking, if you look at the different possible places that Mercury can be, you see how small Mercury's orbit is? If Mercury is here, it's at inferior conjunction. If Mercury is here, it's starting to, you can now see it a little at angle from the sun. Mercury here, 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 here. When Mercury is here, this is about as far from the sun that you can see it. As a matter of fact, this forms a 90-degree triangle. This is a 90-degree triangle right here. That's when Mercury is the farthest from the sun in terms of in the sky. That happens to be 28 degrees. And you can actually prove that using trig. You can say, this is a 90-degree angle. You can say a sine of 28 is opposite over hypotenuse. This is the hypotenuse of the triangle. Okay? And it looks like this. So if you want to prove what the angle is, the distance between the Earth and the Sun is 1 AU. The distance between the Sun and Mercury is 0.38 AU. See, this is the Earth, this is the Sun. So the biggest angle that Mercury is going to be is by virtue of the fact that its orbit is smaller. So sine of theta is equal to 0.38 over 1, opposite over hypotenuse. Then theta is going to be sine inverse of 0.38. You go to your calculator, you punch in sine inverse function of 0.38, you're going to get 28 degrees. That means the most that Mercury can be off from the sun in the sky, it's always 28 degrees in front of the sun or 28 degrees behind the sun. So right now, as the sun is rising, I'm always forgetting west and that's north, this is west, right? This is east, right? Yeah, so the sun is rising this way. So then you're going to have Mercury is basically up in the sky right now. It's either 28 degrees ahead of the sun or somewhere close to 28, you know, or it could be 28 degrees ahead of the sun, or it could be in front of the sun, or it could be behind the sun. That's about the only place it could be in the sky. Venus, same way. 90 degrees. You can make a 90-degree triangle here. You can make a similar equation. You can prove that Venus's angle is 47 from the sun. Okay? You don't need any weird imaginary line deal. Okay? However, Mars can be anywhere with respect to the sun. As we noticed, Mars can be in opposition, opposite to the sun. It could be superior conjunction. Okay? How about if Mars was here? Look at all the weird possible places Mars can be in. How about if Mars was roughly around here? At what angle would it be from the sun? Let me erase Venus so you won't get confused from Venus. So Mars is in opposition. It rises at sunset. Mars is in superior conjunction, rises at sunrise. How about if Mars is here? When does it rise? I chose a particular angle. If you make a triangle, you see? So Mars can be 90 degrees from the sun, right? So what time would it rise? Rises at noon. So when the sun is here, Mars rises. So you can have all the possible potential likelihoods. Sun rises, Mars rises with it. Sun is here at noon, Mars rises, 90 degrees from the sun. You can have the sun over there, Mars rises, and then so on, 180 degrees. So you can have all the possible likelihoods that you could possibly have. The Copernican model explains all the phenomenon that we need to explain without using any kind of weird imaginary line deal, without using epicycles. A lot more elegant theory than the Ptolemaic model.